today we are going to talk about the gas power cycle topic 9.8, particularly the Brayton cycle, right? So we will see that uh, just like the diesel cycle or the Otto cycle, we'll derive the efficiency equation for. We'll see what is the efficiency equation for the Brayton cycle. So before discussing the Brayton cycle in depth, I would like to give you a little bit background of this Brayton cycle. So Brayton cycle, it's basically, it's also another name is the turbine gas turbine cycle. So gas turbine cycle is mostly used in power plant, and I'm pretty sure some of you guys are familiar with this sign just next to the Sunland Park, that we have a power plant, El Paso Electric, and that power plant, it's not using the ideal Brayton cycle, rather it's a modified version. But just to let you know that the power plant has this power plant utilizes this type of cycle or basic working principle of those gas turbine power plant is the Brayton cycle, right, or the modified Brayton cycle. So this is a typical diagram or typical schematic diagram of a gas turbines. It has the turbine section, it has a combustion chamber, compressor, and it has the shaft. So that shaft is basically connected with a generator to generate the electricity, right? So basically, this Brayton cycle or this type of gas turbine used for in two sector. One is that power generation, another is in aerospace propulsion, right? Or um, yeah, aerospace application. So let's go ahead and take a look what is the PV diagram or what is the cycle look like for this gas turbine. So this gas turbine, we can see it's a pretty much a open cycle or open system, right? So this for this particular gas turbine, you can see that this cycle would look like this. So it has a combustion chamber, and it has a turbine, it has a compressor, and it has a shaft, right? So basically, if we draw this gas turbine in terms of this cyclic diagram, then it will look like this open cycle gas turbine. So it will be open cycle gas turbine, right? um, Open cycle gas turbine. However, in ideal case, instead of keep it open, if we want to close it, make it a closed system, right? Closed cycle gas turbine, then we will see that instead of taking the fresh air, we'll just recirculate that air, right? So for example, if we start at one with compressor, then it will go to the heat exchanger, and then where Q in will come as the input, and then it will circulate through the heat exchanger where the Q out is rejecting the heat, and then once it cools down, then again the cycle it's continuing. So this is mostly for ideal cases. However, in real cases, we see a lot of times the open cycle, right? So this ideal case is known as the Brayton cycle, Brayton ideal cycle. So let's go ahead and see that what is the PV diagram look like, or what are the things important things about this ideal Brayton cycle. So first thing is that ideal cycle has four different is process, right? 1 to 4. So ideal cycle has four process. Process 1 to 2 is isentropic process, isentropic compression, right, in a compressor. And then process 2 to 3 is constant pressure heat addition. Process 3 to 4 is isentropic expansion. Process 4 to 1 is constant pressure heat rejection. heat rejection, right? And then compression is happening in compressor, right? And expansion is happening in turbine, right? So now the PV diagram and TS diagram of that ideal cycle will look like this. So it will be PV right. So it will be 1 2 3 4. Let me draw this one too. Okay, so it will be 1 2 3 4. Basically we saw that 2 to 3 is heat addition Q in, right? Q in, and 4 to 1 is Q out. 4 to 1 it's Q out, right? So in this process we can see that this is the isentropic process 1 to 2 and 3 to 4, right? So 1 to 2 is isentropic, is constant, constant, and 3 to 4 is also isentropic, is constant, right? So we know that where is Q in and where is Q out. So from this diagram we should be able to derive that efficiency equation. So since it's a closed system or ideal closed cycle, right? So if we do the energy balance, it will become Q in minus Q out plus W in minus W out equals to heat exit minus heat inlet, right? So basically it will become, so we can see that the Q in here in this diagram, in the TS diagram, or maybe in this PV diagram, Q in is basically this 2 step, right? So 2 to 3 step. So that means that Q in will be H3 minus H2, which is nothing but Cp, and it's a constant pressure heat addition, right? Constant pressure heat addition, that's why we are writing Cp minus T3 minus T2, right? And then Q out is H4 minus H1, which equals to constant pressure heat rejection Cp, and T4 minus T1, right? So we know that Q in and Q out, basically we can get the Brayton cycle efficiency, right? It's a thermal efficiency of Brayton cycle, which is equals to W net work output divided by Q in, right? So which is 1 minus Q out over Q in, right? So if we write this, it will be T4 minus T1, and it will be Cp of T3 minus T2, right? So basically this expression will look like 1 minus T4 minus T1 T3 minus T2 eta thermal efficiency. So this is the basic expression. However, if we want to express it in terms of the compression ratio, right, and then this equation will become if we want to express it in compression ratio, then we have to write this expression like we have to take it T1 out. So T1, if we take the T1 out from this expression, it will become T4 divided by T1 minus 1, and then T2 out, it will be T3 divided by T2 minus 1, right? So basically thermal efficiency of this one. So from this process 1 to 2, right, basically if we look at this process here 1 to 2, it's an isentropic. 1 to 2 is isentropic process, right, isentropic compression process. And then for ideal gas, if it is ideal gas and isentropic process, then for process 1 to 2 and as well as 3 to 4 is also isentropic, right? And through isentropic and ideal gas, we know that P2 equals to P3 and P4 equals to P1 from the PV diagram. So now we know that relationship T2 divided by T1 for process 1 to 2 will be P2 over P1, which is equals to K minus 1 divided by K, right? So we know this relationship, which is P3 divided by P4, because P2 equals to P1, P2 equals to P3, and P1 equals to P4. So that means it will become K minus 1 divided by K and T3 divided by T4. So if we plug in all those values, then thermal efficiency of that Brayton cycle will become 1 minus 1 over Rp times not times, the power actually, K minus 1 divided by K, right, Rp power K. So here we got another new term. So in Otto cycle we defined R, in diesel cycle we defined Rc. Now here we got Rp, right? Rp is the pressure ratio. So this pressure ratio is equals to P2 divided by P1. That means if we look at this diagram, PV diagram, right here, so before compression the pressure ratio is nothing but the pressure before compression and after the compression, right? So in the compressor, so the after the compression divided by before the compression, so that's the pressure ratio. And we know that K is the Cp divided by Cv, right, specific heat ratio. So that's all about this the efficiency expression of the Brayton cycle. Let's take a look at the development of the gas turbine, right? How this gas turbine development is evolving by utilizing the Brayton cycle. So development of gas turbine is based on the Brayton cycle is happening in three different ways, three particular ways. One is excuse me. One is that increasing turbine inlet. So for example, if we go back here, we can see that if we can increase the turbine inlet temperature, for example here, TS diagram, the turbine inlet is 3, right? So if we can increase this 3 much higher, then we'll have this if cycle efficiency is higher, right? So that means increasing the turbine inlet. However, if we keep increasing the turbine inlet, that if we make it like too much high temperature, then chances is that it will deteriorate, or it will have bad impact, negative impact on the turbine blade, right? So every material has some specific limitation on handling the temperature, so high temperature. So that's why we need to make sure that we are heating up the turbine in such a temperature that turbine material can survive at that temperature, right? So that is one thing. And then second important thing is the increasing the efficiency of turbo machinery components, right? And then third, so let me talk about this one, how we are increasing the turbine efficiency. So we instead of using the state of the art like CAD cam, or the design or analysis, CFD analysis, we are designing new different type of blades, right, for the turbine blades. And also we are designing different type of like improved compressor. So basically improvement of the turbine and the compressor component is increasing the efficiency of this Brayton cycle, right, or the gas turbine system. And then another thing we are doing, or we'll see later of this chapter, that we modify the Brayton cycle. So basically the adding modification to the Brayton cycle, to the basic cycle. That means that we discussed about the basic cycle. In upcoming class we'll discuss about the modified cycle. So that's all for today, and we'll come up with the modified cycle in the next lecture.